So I'm going to use this interactive tool that is Kaggle. So Kaggle allows you to have codes in Python, codes in R. I'm going to actually put on here on the, I think I may need to stop sharing. No, I can actually type on here. So I'm sharing with you the address of this notebook. You can open that link in your browser, and then you will be able to walk through the tutorial. However, to reproduce it, you will have to have an account on Kaggle, right? So you will, without an account, you can see the actual outputs from the models and everything. But to actually run the codes, as in this example here, where you can actually run the codes, you will have to have an account, and you will have to register your phone number, and then you will need to basically here in settings allow the internet connection, right? So once you have that, you're good to go. So this is interactive. You can run codes online. You could have you can even use GPUs, so you can speed your codes using that. So you don't have to have R or Stan or anything like that. Just using these notebooks, you can actually try the tool. So, all right. So on this tutorial is basically, we are going to talk about how do you visualize data from stream networks in space and time, then how we fit models, how we make predictions, and how we compute probabilities from the outputs. So the first part is like we will have to load some R packages that we need. And then that's pretty easy. In the second part, we're then going to install SSM base. That is the R package that is going to allow us to fit these Bayesian models, right? So for those who are online on the Zoom, if you have any issues reproducing the codes or any questions, happy to answer while I am explaining. So the first part is that we're going to use an example, like a toy example, from the Clearwater River in the US. We're going to use a few spatial locations. So the first thing that we're going to do is to import that. So we are going to import a special stream network object that is basically safe on your session, in your R session. And then once we have that, we then are going to import this data frame called clear, that it has the response variable, temperature, and then a group of covariates. So the first thing that we're going to do is to visualize. So for example, you can visualize your data in a time series format. So you can see there that we have testing data and training data. You could also visualize your data using panel format. So you have then the 18 spatial locations across all the time points. And then this is basically the temperature value. We can as well then use some of the functionalities from the R package, basically collapse this special stream network object. And then we can visualize it using something like a ggplot. So you can produce a plot like this of your network. So you could use all the potential of R and all the potential of ggplot basically using this tool after collapsing your special object. So once we have that, then we go into the fun part, right? So we are going to do like the actual modeling. So the core function on the package is called SSM base, and it's going to work on the following way. So similar to all the models that you have fitting R, you need a formula specifying temperature as a function of some covariates. And then we are going to then let the function know that we are going to find those covariates in this data frame called clear. And then we have to basically establish a path so that the function finds basically things within the SSN object, such as matrices that will let us know if points are flow connected, for example. So then there are a lot of functions options for modeling the temporal part. So you will have an autoregressive process that is pretty simple. So we specify the temporal part just using a list where we say, well, this is an autoregressive process. And the column that we are going to use in the data frame is called date. And then to specify the special part, we then say, well, use this SSN object, and then use this covariance matrix. There are plenty of options that you could find on the help of the R package. And then the rest of it is just like how many iterations do you want, how many chains, and etc. So a question that people ask is like, what happens if I don't have a special stream network object? If my data is just spatial temporal? So on here, on this space method, if you pass as an argument no SSN, and then you could use covariance matrices such as Euclidean distance. So basically, it's going to use whatever is available in the literature. You could basically use it. You don't have to have a special stream network object, right? So that takes a few minutes. So normally takes running that approximately 6 minutes. Once you have the model fit, then you could do a lot of cool things with that. So you can basically run a summary statistic. So you could basically are going to get a measure of the special parameters on there, also the covariates, and you're going to get some predictions as well, right? So one of the things that we can do as well is we can plot the actual outcome from that. So for example, these are the regression coefficients, just to make sure that the model converge. We can look as well at the spatial parameters. So basically see how much spatial correlation is out there, what is the spatial range, and what is the node effect as well. For example, if you want to see how much temporal autocorrelation, this plot basically shows you the amount of temporal correlation. So if there is a lot of temporal correlation, then this parameter phi is going to be really large. And then you might be thinking, well, how can we make predictions with this? So there are two main ways. So one way is the model is going to automatically impute whatever is missing. If there are missing data in the time series, the model imputes the values. So, and then the other way is just making predictions. If you say, okay, I have a big network, I want to make predictions in the full network. So I'm going to show afterwards that function. So here we can easily compare how good are the predictions from the model. So this plot on here has the true temperature values that we held out compared to what is predicted from the model. If the predictions are perfect, then all of these points will be falling on the diagonal line, but they are, they are pretty good. And we have as well uncertainty around them, right? Which is something that people really like to have, uncertainty around the estimates. Here we have the same, but in the time series format. So basically, the model is going to impute whatever is, fill the gaps, basically, in time. And you can also compute like a root mean square prediction error, right? So basically assess how good is the model. All right, so to my, now I'm going to show you briefly how to make predictions. So let's say that you fit the model, but then you want to make predictions in some other areas. So basically, as we do in R, we use the function predict. We are going to pass to that function the object that we fitted above. And we are going to specify the path as well. And we need to specify a data frame with the prediction locations and all the covariates and all the other things. And how many samples do we want to draw from that. And that works pretty fast. Normally takes like 30 seconds. And then you get something like this one. So basically here in red, we have the observed data. And then in blue, we have predictions from the rest of the network. This is basically this plot on here. Oops, it's too. So on this plot on here, originally I had only 18 spatial locations, and now I'm making predictions here. The diamonds are predictions that I made in the network. And we can also make a compute exceedance probabilities. So as I showed on my initial presentation this morning, we can use a limit of 13 degrees, for example, and then compute the probability of exceeding that. So basically here is a plot of the probability of exceeding the 13 degrees threshold. So yeah, that's basically it. Basically with this R package, you can fit model, visualize your data, make predictions. What is next is that we are going to implement within this framework our anomaly detection process. So yeah, keep tuned, and we will basically keep updating these notebooks. One nice thing is you could get comments. I got my first comment on there. So you could get feedback from people, which is really good. And you could share data. So I think it's a really good resource for sharing research. So if you want to send this to your colleagues, please feel free. And if you want to test it in your computer as well, please let me know if you run into any issues. I'm happy to answer questions.
Awesome. I already sent it to the whole team.
Oh, thank you. Yeah.
So, does anyone have any questions online?
I have a question.
In person, Katie's going.
I asked you a little while ago and I can't quite remember the answer. Does this work for one time slice, so a spatial model? So this looks amazing and I really want to implement it, and I can't quite remember the reason for not at the time.
That is a good question. The answer is yes. So basically, a special process is only when you have only one time point. So it will basically fit the model for just a special process. Yeah, the answer is yes. Yeah.